Hello everyone, in this particular video I am going to discuss reactivity of group 16 elements towards halogens. Group 16 elements form different kinds of halides with halogens. These are number 1 Hexa Halides, EX6, number 2 Tetra Halides, EX4, number 3 Dialites, EX2, number 4 monohalides, E2X2. I will discuss all these halides one by one. First, I would like to discuss Hexa Halides. Now, what are group 16 elements? These are oxygen, number 2 sulphur, next selenium, tellurium, last polonium. Oxygen belongs to second period, sulphur third, selenium fourth, tellurium fifth, polonium sixth. Oxygen does not form hexa halides. Why does it happen? Because oxygen has only 4 orbitals in its valence shell, as it belongs to period 2. These are 1 twice s and 3 twice p orbitals. These 4 orbitals can accommodate maximum 8 electrons. 8 electrons mean 4 bonds. So, second period elements can form maximum 4 bonds. Therefore, their maximum covalency 4. They cannot form bond more than 4. In hexa halides, oxygen has to form 6 bonds with 6 halogen atoms. It means oxygen has to accommodate 12 electrons in its valence shell, which is not possible because oxygen does not have any vacant d orbitals to keep extra electron in its valence shell. Therefore, hexa halides of the type OF6 does not exist. Due to the absence of vacant d orbitals in the valence shell of oxygen. Okay, next, polonium also does not form hexa halides. Why? In hexa halides, the oxidation state of central atom is +6, but due to inert pair effect, the stability of +6 oxidation state decreases from oxygen to polonium. The +6 oxidation state decreases. +6 stability decreases due to inert pair effect, but +4 stability increases from oxygen to polonium. It means polonium tends to show +4 oxidation state, which is the maximum oxidation state of polonium. Therefore, polonium does not form hexa halides as it does not show +6 oxidation state due to inert pair effect. So, only sulfur, selenium, tellurium, these three elements of group 16 can form hexa halides, but they form hexa halides of fluorides. They form only hexafluorides, hexabromides, hexachlorides, hexaiodides of sulfur, selenium and tellurium do not exist. SF6, SeF6, TeF6, only these three hexafluorides exist. Okay, hexachlorides, hexabromides and hexaiodides do not exist. So, why these three elements sulfur, selenium, tellurium form hexafluorides? Because they have vacant d orbitals. Sulfur, selenium, tellurium have vacant d orbitals, so they can expand their octet. They can expand their octet means they can accommodate more than 8 electrons by using their vacant orbitals present in their valence shells. Polonium also has vacant d orbitals, but it cannot expand its octet because the +6 oxidation state is not stable. In these elements, they have vacant d orbitals and their +6 oxidation state stable, so they can form hexa halides, but only one kind of hexa halides exist in these elements, that is hexafluorides. Why does hexachlorides not exist? Why does hexabromides not exist? Why does hexaiodides not exist, though these elements have vacant d orbitals? So, presence of vacant d orbitals alone does not decide whether an element can expand its octet or not. There are two more factors that we must consider. These are number A, EX bond strength. Number 2, steric crowding. These two factors also decide whether an element forms or expands its octet or not. How? Let me take the examples of SF6 and SCl6, sulfur hexafluoride and sulfur hexachloride. It is not exist, okay? It exists. Why? Question. In both these compounds, the central atom is sulfur. Okay? But the terminal atoms are different. In sulfur hexafluoride, it is the smaller size of fluorine atoms. but in case of sulfur hexachlorides, it is the bigger size of chlorine atom. So sulfur can easily accommodate 6 smaller size of fluorine atoms. There would be no steric crowding, okay, as you can see. But in case of sulfur hexachloride, 6 bigger chlorine atoms cannot be accommodated around the sulfur. Why? Because steric crowding will take place around the sulfur. Okay. This steric crowding does not allow 6 chlorine atoms to be accommodated around sulfur. And next one is weaker bond strength. How? Because the bond length, it is the internuclear distance between two atoms. The bond length is longer in case of sulfur hexachloride, but in case of sulfur hexafluoride, the bond length is shorter because the size of fluorine atom is smaller compared to the size of chlorine atom. So sulfur chlorine bond strength is weaker compared to sulfur fluorine bond. Weaker bond means less stability. It means sulfur hexachloride is unstable due to weaker sulfur chlorine bond, and this is stable compound due to strong sulfur fluorine bond. Therefore, this compound exists and this compound does not exist. Not only hexachloride, hexabromide, hexaiodide compounds of sulfur, selenium, tellurium do not exist due to these two factors. Okay. Steric crowding results due to the bigger size of chlorine, bromine and iodine. Okay. Next we discuss the structure of hexafluorides of sulfur, selenium, tellurium. So in hexafluoride, the central atom is bonded to 6 fluorine atoms, is it not? Suppose sulfur, it is bonded to 6 fluorine atoms. So what is the hybridization of sulfur? It is sp3d2. Why? Because in this compound sulfur is forming 6 sigma bonds and there is no lone pair on the sulfur atom. Why? Because sulfur has 6 valence electrons and all the 6 valence electrons are involved in bonding. Therefore, there are no lone pair of electrons on sulfur atom. So 6 sigma bonds means what? 1s 3p 4 orbitals, 2d 6 orbitals means sp3d2 hybridized. So SF6, SEF6 and TEF6, all these compounds have octahedral geometry. Octahedral geometry. Okay. Octahedral geometry. Suppose it is E. 6 fluorine atoms where E is the sulfur, selenium or tellurium. Okay. Next we discuss hydrolysis of these three compounds. Okay. Hydrolysis of sulfur hexafluoride, selenium hexafluoride and tellurium hexafluorides. Sulfur hexafluorides does not undergo hydrolysis. Why? As F6 does not undergo hydrolysis. Okay, why? These two undergo hydrolysis, but sulfur hexafluoride does not undergo hydrolysis. Why? Let me draw the structures of these three elements. In all these elements, the central atom is different, but the terminal atoms, that is fluorine atoms, are same. Okay, so as we move down the group, the size of central atom increases from sulfur to tellurium. It means the size of sulfur is smaller compared to selenium, which in turn is smaller compared to tellurium, selenium, sulfur. All these three central atoms are surrounded by 6 smaller size of fluorine atoms. So in hydrolysis reactions, as we know that it is the oxygen atom which attacks. Okay, so oxygen atom attacks the central atom because oxygen has lone pair of electrons, so it can donate its lone pair of electrons to the central atom. As a result, a reaction takes place known as hydrolysis. But in case of sulfur, you can see the sulfur atom is protected by 6 fluorine atoms. There is no room for oxygen atom to attack the sulfur. There is no room, or you can say there is no open space for oxygen atom of water to attack the sulfur atom. But in case of selenium hexafluoride, oxygen atom finds some room to attack the selenium, so it can attack selenium easily compared to sulfur hexafluoride. But in case of tellurium hexafluoride, oxygen atom finds more room, or you can see more space to attack the tellurium atom. So which molecule is supposed to be more reactive towards hydrolysis? It is tellurium hexafluorides. Why does it happen? Because the size of tellurium atom is bigger compared to selenium and sulfur. Therefore, water can easily attack this tellurium atom, and these 6 fluorine atoms do not protect tellurium to a great extent as they protect sulfur. Okay, these 6 fluorine atoms protect the sulfur in a great extent, which is not the case in tellurium hexafluoride. Therefore, rate of hydrolysis is in the order SF6, SEF6, TEF6. Tellurium hexafluoride undergoes hydrolysis. Do you know what is the product of tellurium hexafluoride? Hydrolysis product of tellurium hexafluoride. TeF6 with water gives rise to A6TeO6 plus HF. This is the product. Balance the reaction. 6. So this is the product of tellurium hexafluoride with water. Okay. Next we discuss Tetra Halides. Now I discuss number 2, Tetra Halides. EX4. Except oxygen, all the group 16 elements form Tetra Halides. Now you must be thinking that oxygen has ability to form 4 bonds. Then why Tetra Halides of oxygen do not exist? Suppose OF4 exists. Suppose OF4 exists. So in this compound, oxygen has to form 4 bonds with 4 fluorine atoms. Oxygen has 6 valence electrons. Out of 6 valence electrons, 4 electrons are involved in bonding with 4 fluorine atoms. It means this oxygen has now 2 non-bonding electrons, which means 1 lone pair of electrons. Now count the number of electrons present around the oxygen atom. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons. Oxygen cannot accommodate 10 electrons. It can accommodate maximum 8 electrons in its valence shell due to the absence of vacant d orbitals. That's why oxygen cannot form Tetra Halides. But Tetra Halides of other group 16 elements exist. Let me consider some examples. Sulphur tetrafluoride, sulphur tetrachloride, selenium tetrafluoride, selenium tetrachloride, tellurium tetrafluoride, tellurium tetrachloride, tetraiodide. Similarly, polonium tetrachloride, polonium tetrabromide. These are some examples of known tetrahalides of group 16 elements. Okay, now I discuss their geometry. I discuss the geometry of SF4. In SF4, sulfur is forming 4 bonds with the 4 fluorine atoms. Sulfur has 6 valence electrons. It means it has now 2 non-bonding electrons, as the 4 electrons are involved in bonding with 4 fluorine atoms. Okay. Now count the number of sigma bonds and lone pair. 1, 2, 3, 4. 4 sigma bond. 4 sigma bonds plus 1 lone pair. How much? 5. Okay. Now take 5 orbitals. 1s, 3p. We need 1 more orbital, that is d. sp3d hybridization. Okay. So in tetrahalides, the central atom is sp3d hybridized. It means they all have trigonal bipyramidal geometry. SF4, trigonal bipyramidal geometry. In trigonal bipyramidal geometry, these 3 bonds are called equatorial bonds, and these 2 are called axial bonds. It means these 3 are equatorial positions and these 2 are axial positions. Always remember, if any element is found to be sp3d hybridized and that element has, suppose, lone pair of electrons, then we should put the lone pair of electrons at the equatorial position, not at the axial position. As SF4 has 1 lone pair of electrons, so we must put that lone pair of electrons at the equatorial positions. So I have put at these positions. Now put the 4 fluorine atoms. 2 are at axial positions and 2 are at equatorial positions. What about the bond length of 4 SF bonds in SF4? Are these all 4 sulfur fluorine bonds identical? Not. Are not identical. Why? Okay, why? Let me explain. Suppose these 3 are equatorial positions and this one is lone pair of electrons, suppose. Okay, equatorial positions, 2 sulfur fluorine bonds and this one is lone pair of electrons. This is the 4th position, axial position, and this one is 5th position, axial position. Now these 2 axial bonds suffer 1 lone pair repulsions and 2 bone pair repulsions. Okay, these 2 axial bone pairs suffer 1 lone pair repulsion and 2 what? Bone pair repulsion. Okay, in turn 2 equatorial bonds, okay, suffer 2 repulsions from 2 axial bonds. I mean, these 2 axial bonds suffer one lone pair repulsion, suffer from one lone pair repulsion and two bone pair repulsions. Okay. In turn, these two equatorial bonds suffered two repulsion from two axial bond pairs. Okay. Two axial bond pairs suffered repulsion from one lone pair and two equatorial bone pairs. Is it not? Okay. One repulsion, two repulsion. Okay. And this is also lone pair bone pair repulsion. On the other hand, two axial bond pairs, two equatorial bond pairs suffered two repulsions from two axial bond pairs. Is it not? So, which bonds suffer more repulsion? Of course, these are axial bond pairs. They suffer more repulsion. They suffer one lone pair repulsion and two equatorial bond pairs repulsion. But equatorial bonds suffer only two repulsions from two axial bond pairs. As axial bond pairs suffer more repulsion, so they get elongated to minimize the repulsion. That's why all the sulfur fluorine bonds in SF4 are not equivalent. Okay. Next, there is a question about hydrolysis. SF4 undergoes hydrolysis. But SF6 does not undergo hydrolysis. Why? Very simple questions. SF4. In both these compounds, the central atom is same as well. The central atom is same as well as the terminal atoms. Okay. So in this case, the central atom is sulfur. Here also sulfur. This sulfur is surrounded by four smaller fluorine atoms. 1, 2, 3, 4. In this case, 6. Okay. So hydrolysis means what? Reaction with water. In water, oxygen has lone pair of electrons. So in SF4, this oxygen gets more open space to attack the sulfur. In case of SF6, oxygen does not find any open space to attack the sulfur atom, because these 6 fluorine atoms protect the sulfur atom from the attack of water molecules. Okay, do not attack. 6 fluorine atoms protect the sulfur atom from the water molecules. In this case, 4 fluorine atoms cannot protect the sulfur from the attack of water molecules. So water molecules can easily approach the central atom. As a result, SF4 undergoes hydrolysis. So what is the hydrolysis product of sulfur tetrafluoride? SF4 on hydrolysis gives sulfur dioxide and 4 HF, 2 water molecules. This is the hydrolysis products of sulfur tetrafluoride. Next, I discuss dihalides. Now I discuss dihalides. Number 3, dihalides. EX2. Except selenium, all the group 16 elements form dihalides. Let me consider some examples of dihalides. Oxygen dichloride, sulfur dichloride, dibromide, tellurium dichloride, dibromide, diiodide, polonium dichloride, dibromide, diiodide. These are some examples of dihalides. Now I discuss their geometry and shape. EX2. Here E is the central atom and it is forming 2 bonds with 2 halogen atoms. As it is group 16 element, therefore it has 6 valence electrons. Out of 6 valence electrons, 2 electrons are involved in bonding with halogens. It means this atom has 4 non-bonding electrons which are equal to 2 lone pair of electrons. Now look at the number of sigma bonds and lone pair of electrons. 2 sigma bond and 2 lone pair of electrons. It means 4. So we need 4 orbitals. First we take 1 s orbital, then 3 p orbitals. It means the central atom in dihalides is sp3 hybridized. Okay. There are 4 electron pairs around the central atom. Electron pairs includes both lone pair plus sigma bond pair. Okay, both. Now 4 electron pairs means tetrahedral geometry. Okay, tetrahedral geometry. But while we decide shape, we do not consider lone pair of electrons according to Weissenberg theory. Okay, so if you do not consider these 2 lone pairs, then the shape would be what? V-shaped. Is it not? V-shaped. So these dihalides have V-shaped structure, or you can say band shaped structure. So they all have V-shaped structure or band shaped structure. But the electron pair geometry is tetrahedral. No doubt, electron pair means what? Electron pair includes both lone pair plus bone pair. That's why it is tetrahedral geometry for electron pair geometry. But while you consider the shape, you don't need to consider lone pair of electrons. Just consider the bone pair of electrons. Okay. Next, I discuss bone angle in water and oxygen difluoride. Water, H2O, oxygen difluoride. In both these compounds, the central atom is oxygen. But the terminal atoms are different. In water molecule, between oxygen and hydrogen, which one is more electronegative? Of course, it is oxygen. Therefore, the bone pair electrons lie nearer to the oxygen. Is it not? In OF2, between oxygen and fluorine, fluorine is more electronegative than oxygen. Therefore, bone pair electrons lie nearer to the fluorine atoms. So, in which bone pair repulsion is supposed to be more pronounced? In which case? Definitely here, because these two bone pairs are more close to each other. In this case, these two bone pairs away from each other. Is it not? Therefore, bone pair repulsion is less. Here, bone pair repulsion is more. More is the repulsion, greater is the bond angle, according to V.S. theory. It means water molecule has more bond angle compared to oxygen difluoride, and the bond angle in water is found to be 104.5 degree. In case of oxygen difluoride, it is found to be 103 degree. Okay, because it has less bond pair repulsion. Okay. Next I discuss monohalides. Number 4. Now, number 4, monohalides. E2, X2. All the elements of group 16 form monohalides. Some examples are O2F2, S2F2, S2Cl2, Ac2Cl2, so these are some examples of monohalides. You must be thinking the formula of monohalides should have been EX, but they are written as E2X2. They do not exist as EX, they exist as E2X2. Why does it happen? Well, Let me explain. Suppose sulfur forms one bond with chlorine. Sulfur has 6 electrons in its valence shell. It has 6 electrons in its valence shell. Out of 6 electrons, 1 electron is involved in bonding with chlorine atom. It means it has 5 non-bonding electrons. Chlorine is forming how much bond? 1 bond. And it has 7 electrons in its valence shell. Out of 7 electrons, 1 electron is involved in bonding. It means this chlorine has 6 more non-bonding electrons. Now count the number of electrons around sulfur and chlorine. Chlorine has 8 electrons. It means it is fulfilling octet, but sulfur has 7 electrons. It is not fulfilling octet. It has one unpaired electron. How? This electron is paired up with this electron. This electron is paired up with this electron, but this electron is odd electron, or we can say unpaired electron. No element tend to have unpaired electron because element with unpaired electron is not stable. Okay, so no element wants to have unpaired electron. Therefore this sulfur, what it does, it forms a bond with another HCl unit. Okay, forms another bond so that this unpaired electron gets paired. So when this bond is formed, you can see now all the electrons of sulfur are paired and fulfilling octet. How? 1, 2, 3, 4, 5, 6, 7, 8. Also this sulfur is stable. 1, 2, 3, 4, 5, 6, 7, 8. Therefore monohalides do not exist as EX. They exist as E2X2. It means they undergo dimerization. What do you mean by dimerization? If two molecules combine together to form one molecule, it is called dimerization. Dimerization. Okay. So in case of monohalides, two EX units combine together to form E2X2. It is called dimerization. Okay. Now I discuss their structure. Their structures are similar to hydrogen peroxide. What is hydrogen peroxide? H2O2. This is the structure of hydrogen peroxide. Also monohalides have structure like hydrogen peroxide. Hydrogen peroxide. Okay, this is the structure of E2X2. All the monohalides have structure like this. This is called open book structure. Okay, open book structures. Now monohalides undergo disproportionation reaction. How? Let me consider an example. Ac2Cl2. It undergoes disproportionation reaction on heating and gives selenium and AgCl4. In monohalides, the oxidation state of selenium is +1. In this case, it has 0 oxidation state, but in this compound it has +4 oxidation state. Okay, that means selenium gains electrons and loses electrons. It means this compound undergoes oxidation as well as reduction, and this kind of reaction we call disproportionation reaction. So we can say that monohalides undergo disproportionation reaction. It is an example of disproportionation reaction of selenium monohalide. Up to here, reactivity of group 16 elements with halogens is over. Okay, next we discuss allotropes of phosphorus and sulfur. Thank you.